Hello, my friends. Yeah, today's is a very unusual topic. Scary for me. So sorry for the fuck-ups. So why do we have 7 nodes? I will try to give a simple mathematical explanation of this topic. What nodes we are talking about, not some remarks on paper, but about musical notes. This question, so why 7? Why not 6? Why not 8? Why not 10? Why 7? This question actually is tricky because it's not true. We don't have 7 notes. In fact, we have 12 notes if we count black notes as well. You know, black notes matter. They are called do, do diez, re, re diez, mi, fa. It's kind of legacy. We don't have mi diez here. Diez basically means like and half. Do, do and half. Re, re and half, like that. And 12 also is not correct. It's not true. Actually, we have, how many notes we have? Who knows? Infinity. Yes, infinity, it's right answer. But if we count maybe these notes that our ear can hear, like something like that, around that. Anyway, the question is why do we have 7 notes like do, re, mi, fa, sol, la, si, you know, yeah? My goal is to explain this complex topic, a complex thing with a very as simple language as possible, with a simple language, because the correct answer actually you can find on Wikipedia. There is a correct answer. Why do we have 7 notes? The problem is that it's a little bit hard to read this answer because the explanation starts with some mathematical formulas, then it continues with some next mathematical formulas, you know, logarithm, then it continues, then it continues, then it continues, and finally we got the answer. This is why we have 12 notes. A little bit complicated, right? So I will try to explain the same topic like in a simple language using a little bit programming. Okay, yeah. So let's start from a small demo. One thing, I think that I want to demonstrate, like one basic idea is that every note is actually a number. Every note is just a number. So let's try to demonstrate it. Let's play some well-known song like Metallica, right? You know Metallica? Nothing else matters. Let's try. Yeah. Oh, sorry. You like Metallica? No, me too. No. I don't like Metallica. Sounds more like Nirvana, right? What is the problem? Who knows? What's the problem here now? Yes, guitar is not tuned. Guitar is not tuned. And now we need to tune the guitar. To play well, we need to tune the guitar. Usually we use some devices like this or some mobile applications like this. What it does, I start pulling the note and this thing like moves and shows me should I relax the tune. If I relax it, then the tone gets lower. Technically speaking, the frequency of this sound wave like goes down. Now sound wave is maybe like 100 times in a second, and if I strengthened the string, then sound wave comes upper and upper, and now the frequency of this sound wave is maybe 200 hertz or times per second, something like that. So now I need to look at this application or this device and tune all the strings to exactly these numbers that it's saying to me. The next string. Next string. This is called tuning. We are almost there. Something like that. And the last string. Okay. Now it should be tuned, so it should sound better. Let's try. Helps. So now it sounds better. It was called tuning of a guitar. What I was trying to show that basically every note is a number. This number. This number shows how many hertz or how many times in a second sound wave like moves, hesitates. I don't know. Yeah, fluctuates. Yeah. Okay. And when we put all the notes to the correct numbers, then the instrument works well, sounds nicely. So the question is, the question is who said exactly these numbers? Who said that one note should be this number, another note should be that number? Who said that? Why? Why exactly these numbers? Once again, every note is just a number. Name of the note doesn't matter. Color of this key, white or black, doesn't matter. The only thing that matters is frequency of the sound wave, and nothing else matters. This number, this is the only important thing about every note. Currently, in our usual music system, we have 7 notes, or 7 notes that are called do, re, mi, fa, sol, la, si, do. Do is like next do. And every note has a very specific number near it. This is the frequency of this note. You can find these numbers in Wikipedia. Also, just if you didn't know, these notes also have aliases. Just different names. Note La actually is often called A, C is often called B or sometimes H, and so on, C, D, E, F, G. These are just 2 different names for every note. Every note has 2 names, maybe even more actually. You might ask why these names start with La and not from Do. I don't know, it's just legacy. Yeah. There is no answer.
There is an answer, because the simplest gamma in C major is C, D, E, F, G, A. So that's why they started from C, because that's the simplest gamma to play.
But why didn't they start from A? That's a question.
A gamma is much more complicated. It uses black notes as well.
Still, why don't? This is a typical answer of musician. Because and not clear. Okay, why exactly this number? This is a key question. Before we answer our question about 12 notes, why exactly this number? Who said that? And let me try to explain who said that. Why exactly these numbers? Let's imagine sound wave. That here's it's like this one. When I play this note, this is called La, and this is called La, A1, and this is called another La. You can hear that they actually seem very similar. If I press them together, they are very similar. They are pretty much similar. And why they are similar? Compared to other notes, for example, these are different, and these two are very similar. This why they are similar? Because they are sound waves have frequency that is like power of 2. Like one is twice more than another. And when you look at these sound waves, what happens? Like every second time, these sound waves like match each other. They like clap every second time, like 200 times in a second, something like that. And at these moments, our ear is happy. Our ear listens like, very similar. Nice, I like it. So our ear puts like 3 likes for such sounds. They are really beautiful. Or do and do. Or me and me. Like very similar. Yeah, so the rate of this frequency is 2 to 1. That's the answer why they are very similar. If you take a La and yet another La, not this one, but this one, they are also very similar, and the ratio is 4 to 1. Right? This was 2 to 1, this is 4 to 1, like power of 2. And just in case, if you take a little different sound waves with ratio like not 2 to 1, but 3 to 2, for example, they also sound good together. Not so well, but quite good, like this. This is 3 to 2. Not perfect, but still good. If we take, this is, Sol and Do, for example, has this ratio. In this case, our ear is not so much happy, but still quite happy. If we take sound waves like with ratio 4 to 3, this is like this. Again, not perfect, but still quite good. In this case, our ear puts 1 like. Still quite good, but not perfect. And so on, and so on. We can combine like sound waves of frequencies that like match each other with some ratio. So if we try to build, using this knowledge about sound waves and frequencies, we can try to start building our own keyboard from the scratch. How we do it? We can put the initial note like pretty much any note, any sound, any frequency. Many years ago, people picked one specific number, 440 hertz, just because somebody decided that this is a beautiful sound. And they decided, okay, let it be some initial sound, initial number. And we can calculate all other notes starting from this basement. Usually people use this instrument for tuning initial note, because this is a very specific instrument that always generates the same sound. Like, thanks to this form, when you put it, it starts vibrating and always generates the same sound. Exactly this one. It's called, in English, tuning fork. So musicians tune the first number using this tuning fork, and then we can add to our keyboard next numbers. The next note La, the next note La, previous. All they have frequency like 2 times more. Now we have like a keyboard like this. Like perfectly sounding with each other, all these notes. But the problem is that if you have only these notes, it's boring. We cannot play like anything, really much anything. For example, we cannot play like so close, no matter why. Like, no. If we try use 2 different notes, then we try so close, no matter why. Like, boring. We cannot create melodies. We can create music with only this notes. We need to fill the gaps. We need to put something inside. Yes, so we will create our keyboard like putting initial note and the next initial note like do and do, and now we will need to fill something between. And the question is, which frequencies do we need? Which notes do we need to put? Maybe let's try to have a little bit of programming, a little bit of Svelte code. So this is our initial keyboard that is empty initially. Let's try to add the first note, do. Like bass is basically just some number. Like this is current. Oh, sorry, I need to increase the font. Can you see it? Yeah. Bass is just some random number, initial number. Doesn't matter. Doesn't else matters. So let's put note do or C like with bass frequency, and next do with bass 2 basses. Now we have 2 notes on our keyboards like do and next do. We have 2 notes and nothing between. And when I press them together, then we see a ratio of these sound waves. 2 to 1, exactly. Now let's add something between. To play some melodies, we need to fill the gaps. So let's try to add note C, for example. C will have the second perfect ratio. As you remember, it was 1.5. 1.5, right? Now we have note C also. And now we have, and they sound together. It's just because of JavaScript, but technically, yes, they sound like good, let's say. We still cannot play pretty much anything. Now we can add a few more notes. For example, we can add fa, and this has ratio 4 to 3, I guess. Now we have some notes. Still quite hard to play anything. And probably we can add note mi here, which has frequency 5 to 4. Now we can play at least something. It's already something, right? And this way we can add more and more notes. We can add note re, which is and so on. Now we can play. Now we can play. Happy birthday. Already something. Still missing some next note la, something here. But anyway, and so on. We can continue. Now let me revert this part. Now we have all the 12 notes, and you can see ratio of every note here. Now we have the full keyboard. This is how was built layout of music notes like 500 years ago. People used rational numbers for this. Yes. At that time they didn't have TypeScript and Svelte. So the answer is that they filled the gaps with rational numbers, like 3 to 2, 4 to 3, and so on. And they sounded like quite good. And this tuning or this layout of keys was called natural tuning. There is another option which is called equal temperament, which was introduced quite recently, like 200 years ago, something like that. And this first layout that I show it currently, it's called pure intonation or just intonation or natural tuning. It's very natural for our ear. It uses rational numbers like 3 to 2, which is natural for our ears, and that's why it sounds very good. Let me just repeat that. Yeah, these notes at do, re, mi, fa, sol, la, si, they have all these rational frequency ratios, like that. This system sounds perfect, sounds very good, very natural for our ears. Getting back to the question, why do we have 7 notes? In this system, theoretically, we are not limited to number of notes. Theoretically, we can add more and more notes. We can always add some new note here, like creating some 12 to 7, something like that. And we can add more and more notes here in between the gaps. So here we did not have any limitation of number of notes. But nowadays, people don't use the system, and that's why. The system is perfect. It sounds perfect for our ears, but it has one disadvantage. Scalability. This system is not scalable in that sense that we cannot take any melody and shift it up. Like we usually do in guitar. When my voice something is like, every day, ba 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 ba, but voice of some other man might be like higher, and then he would need to shift up all the melody and play something like that. Every day, da 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 da. Another girl might sound like every day, da 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 da. Like it's called, oh, it's called. No, it's like moving melody upper and down and lower. We have this word here, transposition. It's called transposition. So we can take, you want to take any melody and be able to move it upper or lower. Like nowadays people want it. People want to, every like composer who created a melody, he wants not only himself to sing the song, but he wants also others to also hear the song. Other people with very different voices, with very different instruments. We want to scale and move this melody up and down. And with this system, it's not good because now let's try to transpose. If we click do and sol, for example, they have ratio 1 to 1.5, like very good. It sounds perfect, except JavaScript. But if we try to transpose this melody, let's call it melody, and a little bit higher, let's try to this one and this one, like one higher, like was 1.5, a little bit higher, still 1.5, a little bit higher. You see, if I move, we have 2 notes, do and sol, and we move each of them a little bit higher. Now we get now it doesn't sound good. Now the ratio is not 1.5 anymore, but it contains some error, quite big error. And like musicians can hear that this sounds good, but this sounds ugly. This doesn't sound good. This is what we call like it's not transposable. This note system is not transposable. We cannot move any melody up and down. That's why. Do you have any question at this moment? Okay, that's why this natural tuning was perfect, but people created another one, something about 200 years ago, maybe 300 years ago, I don't know. And this is called equal temperament. And for me, this was just a genius idea. What they did, they took natural tuning And they decided, hey, let's introduce small errors to every node, small shift to every node, so that now they are not perfect, but we can transpose, we can shift melody up and down without big errors. That was the idea, to introduce a small error to every node, so that now it's scalable. Not perfect, but scalable. For me, it's genius. And nowadays, it's the de facto standard in America and Europa, I don't know, maybe Japan, maybe whatever else. And just for information, that there are other systems as well in, I don't know, Arabic countries, in India, in Pakistan, I don't know. There are also other systems, but I don't know them. Yeah, I know only these two. Just for information. So, how can we create this equal temperament system? We will start. Yeah, the whole idea is to divide the octave. Octave is this distance between do and do. The whole idea is to divide this octave into equal steps, like equal steps, like in our case to 12 equal steps, so that now these numbers are not rational anymore. So we will start with exactly the same idea, that the first node is just random, just some random specific number. Another do is like two times this number. So first and last are the same, still the same. But we will fill the gaps a little bit differently, with a little different numbers. And the whole idea is that we will use powers of 2. Like this node will be 2 power, so many. It's hard to pronounce in English, sorry. Yeah. So this is powers of 2. So this octave is divided to exactly 12, like how it's called, logarithmic periods or steps or whatever you call it, mathematicians. That was the idea.
Why 12?
Hmm?
Why 12?
Yeah, we will get soon. We will get back to this question. Yeah. This is a root question. So let's try to create a layout with equal temperament, just to demonstrate how it's done. We will put the first node still the same, still base. We will put another do still base 2, but for the next nodes, we will use like power of 2. Here we have 5. Here we have 6, and so on. So we like it's pretty much simple. Like 1, 2, 1, 2, 3, 4, 5, and so on. And now we will have keyboard like this. Okay, let's check this one. Hopefully. Oops, sorry. Something was wrong. Yeah. Thank you.
The power is also on.
Right. Thank you. This is called equal temperament. Yeah. So the sounds are very, very close, actually. Sorry. And if we check, are they similar to the previous note? They are very similar. Like do and do is the same. The next one, very similar. The next one, very similar. Very similar. So our ear almost cannot hear any difference. But you can see that they have a little bit different frequencies, right? A little bit different numbers. And let's now check if this system can be transposed, if this is transposable. If we press do and sol in this system, Oi, this one. This is almost, the ratio is almost 1.5. Not exactly, a little bit lesser, but almost 1.5. With a very small error. With a very small error that our here almost cannot hear. Here. Oh, sorry. And if we try to transpose and move upper this melody, and upper, and upper, and upper, this is a brilliant part. The error is always the same. The error is always very small and always the same. This is thanks to powers of 2. Yeah, these errors. Always small and always the same. This is why nowadays all the music is transposable. We can move any melody up and down with a very small error that we cannot hear, basically. Isn't it genius? Do you like irrational numbers? No? Okay, so, and getting back to the final question. Why do we have 7 or 12 notes? As I said, in the natural tuning, theoretically, we could have any number of notes. We were not limited. But in equal temperament, when we divide the octave to n steps, n notes, we need to find the best n. Like it's basically a mathematical equation, mathematical exercise. How to find the best n, 12, for which the error between our equal temperament and natural tuning would be minimal. This is a mathematical exercise. Sounds complex. For simplicity, we will count error as a difference between perfect ratio 1.5, sol and do in like this natural tuning, between this one and ratio sol to do to our equal temperament note with different n. So let's count this as an error and let's find for which number of keys this error would be the minimal. If we would have 3 notes, if we would divide an octave to 3 notes, then the error would be quite big. If we would divide octave to 5 notes, the error would be a little bit lesser. Actually, we have here all the image. Yeah. If we have 3 notes, error quite big. If 4 notes, error quite big. I just created a loop like for all numbers of keys. 5 errors, much better. 7 notes, even better. But if we are patient enough and scroll down, we can find that if you have 12 notes, 12 keys, then the error is much lesser. Then the error is almost 0. Basically, this is the answer why we have 12 keys. Because in case of 12 keys, the error in our notes is the minimal one, is very small. If we scroll down, the following notes are bigger. So it doesn't make sense to add more and more notes because the error will increase. The minimal error is actually for 12 notes. This is the answer. There is one funny nuance that if we are patient enough and scroll down, we will see that the error can be even smaller. If we had 41 notes, then our notes would be even more perfect, even better. But it would be inconvenient just because of practical reasons, like because we don't have so many fingers. Yeah.
Or if they don't use the notation, use such amount of notes, like 40, around this number. They basically divide, like we have 1 note, but they have 4 notes in this 1 note.
Yeah, we can play like. Technically, our do is here, and our do ds, the next one is, I don't know, here. Like, technically. These are the closest notes on our keyboard, and here they are something like that. And they have like 5 notes more between. They have like 5 notes between this and this. Yes. Is it like practical to play such keyboard? Maybe. Maybe there are instruments in the world that actually do use this thing.
Their own specific instruments.
And actually violin, for example, doesn't have like strict, yeah. So it allows you to move pretty much anywhere. So this was the answer, like, yeah, why the 12 notes is the best one. Yeah, so summary is, the summary is that our tuning system, current tuning system called equal temperament, is not perfect. It's not perfect, but with 7 notes or 12 notes, it's slightly less lame compared to the perfect system. This is the answer. So, yeah, thank you for your attention. There are some references to read more about tuning, notes, and so on, if you want to get familiar with like more information. Thank you for your attention. Live music.
Any questions?
I have one. Do people really use Mac devices to make music? Because that sounded...
Do people use Mac devices? Yes. Of course, people use Mac devices to create music, videos, and so on. This sound is some default sound in JavaScript. It's not about Mac. It's about like how to create sound in JavaScript. I just Googled for the first answer, like new wave run, something like that. Probably there are better ways to create sounds. Yes. I just didn't waste time on it. Actually, I don't know how this generates sounds. This is called synthesizer. It doesn't have any strings inside. It's also electronic music. It has different voices. And I don't know how this generates sounds. Probably not using JavaScript. Yeah. I think.
Maybe just a remark. I saw that actually our voice has no limitation. With our voice we can say call this 14 notes.
Yes.
Also some instruments, let's say violin or some.
Yeah.
Technically it's possible. How about AI? We cannot play so many notes, but AI can play those notes potentially.
Yes.
I think that for AI doesn't even know what means note. AI like knows that these are numbers. Yeah. It can play like 100 times in a second, 200 times in a second. Yeah.
I'm curious what inspired you to learn. I feel like you don't just randomly come across
this topic.
Yeah. What inspired you? Did you start playing and got curious?
No, actually, in my childhood, I got randomly some book, like a very tiny book, explaining this topic, like from a mathematical perspective, with all these formulas. It was very interesting for me. I loved mathematics, but then I realized that I cannot actually explain it to anybody else, and I waited like for 20 years and learned programming in JavaScript, because yeah, at some moment I realized that now I can explain this topic using programming, using some for loops in Svelte. Yeah.
It was a great presentation.
Yeah. Thank you.
The right answer is because of the mistake, because of this error.
Yeah, because in case of 12 notes, we have a minimal error. Yeah.
Can you go religious?
Religious?
You know, who decides how many errors we need?
Sorry.
It's kind of a joke, but I mean, some people are religious, no? Maybe Jesus, you know, decided it's good.
Yes, Jesus, yeah. More questions?
What if you change power of 2 with, for example, powers of E or B or whatever?
I don't know the answer. Maybe people already tried it. Like where there is a lot of like experiments in this area, but yeah, they are not standard yet. I guess. Maybe someday. Power of E and P will be our music, yeah? Maybe.
Next presentation.
Yeah. You are welcome. You can. Actually, I am not professional musician at all. I didn't study in musical school. So if you know more about music, notes, mathematics, you are welcome. Please come here and tell everything you know. Yeah, we will be glad to
Did
see.
you create a project on GitHub for this?
Yes. Yeah.
Do you know about the reason why we don't have black notes between some white notes, I guess?
Yeah, very good question. Why we do have notes between do and re, between re and mi, but we don't have notes between mi and fa? I don't know. The only thing I can say it's legacy. Music current nowadays music is full of legacy. It has very complex notation for writing notes. It's not convenient at all. People call notes like A, B, C or do, re, mi, fa, sol, la, si, and even there they do use different letters. For example, for C note, some people call C note like B, others call it C, H. At the same time, some other people use B for actually C bemol. For some reason, it's full of legacy. Very complicated.
How can we refactor this legacy?
Very good question. Yeah, I would be happy to refactor it. I would be happy to make notes notation much more simple, much more easier to learn. It would be great. Yeah.
So yeah, if you go on YouTube, there are multiple videos on the topic, but it's a rabbit hole. I watched the answer to why there are nodes between nodes, and it's pretty complicated. Just go to YouTube and read all those. Thank you, Andrei. It was.
Yep. Thank you.